This is Cryptography, Lecture 8. I'm going to go over the solutions of the problems on the midterm exam. So let me go to my paper. Yeah, here we are. Problem 1. We have the integers a equal 469, b equals 322. Use the Euclidean algorithm to find the greatest common divisor. So 469 divided by 322, that goes in once and leaves a remainder of, I think, 147. 469 minus 322, 147. 322 divided by 147, that has a quotient of 2. 2 times 147 is 294. 294, 322 minus 294 is a remainder of 28. 147 divided by 28, I think that probably goes in 5 times. That's 140 and leaves a remainder of 7. And 28 is 7 times 4 with a remainder of 0. So the GCD, the greatest common divisor of 469 and 322 is 7. And then we want to work the Euclidean algorithm backwards to write 7 as an integral linear combination of 469 and 322. So let's see. So 7 is 147 minus 28 times 5. That's 147, and 28 is 322 minus 147 times 2. That's 28 times 5. So what is that? I have 147 plus 10 times 147. That's 147 times 11 minus 322 times 5. And 147 is 469 minus 322. So that times 11 minus 322 times 5. So this is 469 times 11 minus 322 times minus 11 minus 5 minus 16. Or I can write this as plus 322 times minus 16. So this is of the form 469x plus 322y, where my x in the solution is 11 and y is minus 6. Okay. So this is working the Euclidean algorithm backwards. Now, there are other linear combinations of 469 and 322 that also represent 7, but this is what comes directly from using the backwards calculation from the Euclidean algorithm. Okay, that's problem number 1. Quick enough. Problem number 2 has to do with a primitive root. So let's say G is a primitive root. This is just the definition. Modulo a prime number P if G to the P minus 1 is congruent to 1 mod P, but G to the K is not congruent to 1 mod P. For all K between 1 and P minus 2. So K is P minus 1 is the smallest positive integer exponent, since that G to that number is 1 mod P. So we want to consider 5 modulo the prime 13. So we have to look at the powers of 5. 5 to the first power is congruent to 5 mod 13. 5 squared is 25, which is 12 mod 13. 5 cubed is, however you want to do it, 125, which if you divide it by 13, I think is 8. Mod 13. So far, so good. 5 to the fourth power, we could just multiply 8 by 5. It's 5 times 5 cubed, which is 5 times 8, which is 40. But 40 is 1 mod 13. So 5 to the fourth power is 1 mod 13. 4 is less than 12. So 5 is not a primitive root. If you do the calculation, 5 to the power 4 is congruent to 1 mod 13. Then we're asked to consider 2 mod 13. So 2 to the first power is 2. 2 squared is 4. Everything is mod 13. 2 cubed is 8. 2 to the fourth power is 16, which is 3 mod 13. 2 to the fifth power is 2 times 2 to the fourth, 2 times 3, which is 6. 2 to the sixth power is 2 to the fifth times 2, which is 6 times 2, which is 12. 2 to the seventh power, 2 times 2 to the 6 is 2 times 12, is 24, which mod 13 is 11. 2 to the eighth power, 2 times 11 is 22, which mod 13 is 9. 2 to the ninth power, 2 times 9 is 18, which is 7. 2 to the 10th power, 2 times 17 is 14. Oops, something's not right here. So let me just double check what I did. 2, 4, 8, 16 is 3, 6, 12. 2 times 12 is 24. 24 mod 13 is 11. 22 mod 13 is 9. Yes. 18 is not 7. 18 mod 13 is 5. 2 to the 10th is 2 times 5 is 10. 2 to the 11th is 20, which mod 13 is 7. And 2 to the 12th is 2 times 7 is 14, which mod 13 is 1. So the first power of 2, which is congruent to 1 mod 13, is 12. All the smaller powers of 2 are not 12 mod 13. So therefore, 2 is a primitive root. And since I already have this table, if I want to find the discrete logarithm of 9 with respect to the primitive root 2 for the prime 13, what power of 2 is 9? It's the 8th power. So you just look at the table. 2 to the 8th is 9, so the log of 9 to base 2 is 8. That's problem 12, problem 2. What about problem 3? Problem 3 is Diffie-Hellman key exchange. So Alice and Bob, over a public channel of communication, have to end up with a key which only they know. So we start with the prime p equal 13, and the primitive root g equal 2, which we just saw as a primitive root. So we have Alice and Bob. Alice's secret key or little number little a is equal to 5. And she computes capital A, which is 2 to the 5th mod 13. 2 to the 5th is 32, which mod 13 is 6. So Alice sends the number 6 to Bob. Bob, meanwhile, his secret key, B, is equal to 7. So the number capital B that Bob calculates is 2 to the 7th mod 13. 2 to the 7th is 11 mod 13. So Bob sends his number B equal 11 to Alice. Now, what does Alice do? She takes the number B and raises it to her, she takes the number B and raises it to her secret key, which is 5. So B to the A, that's going to be 11 to the power 5 mod 13. Let's see, we have to calculate that. Lots of ways you can do it. You start multiplying 11 by 11 by 11, reducing it mod 13. Or you can use the fact that 11 is the same as minus 2 mod 13. So this is like minus 2 to the 5th mod 13, which is like minus 32 mod 13. And minus 32 is the same as 7 mod 13. So Alice ends up with the number 7. What about Bob? Bob takes the number he got from Alice, which is 6, and he wants to calculate A to the power of little b. So A to the little b, A is 6, little b is 7. So Bob is calculating 6 to the 7th power mod 13. Let's see, what is that? I guess we have to do a calculation. 6 is congruent to 6 mod 13. 6 squared is congruent to 36, which is the same as minus 3 mod 13. Because 36 plus 3 is 39. So if 6 squared is minus 3, 6 to the 4th, which is 6 squared squared, is minus 3 squared. 6 to the 4th is 9 mod 13. So 6 to the 5th is 6 times, is 6 to the 4th, which is 9 times 6, which is 36 mod 13. 36 mod 13. Oops, that's not good. Sorry, 9 times 6 is 36. 9 times 6 is 54. Let's see, 13 times 13, 4 times 13 is 52. That looks like 2 mod 13. So somehow I did something wrong, because this number should be the same as this number. So let me double check. Checking is good. The prime is 13, G is 2. Alice chooses her secret number 5 and computes 2 to the 5th. 2 to the 5th is 32. Sorry, let's get back to the beginning. So the prime P is 13. The primitive root is 2. Alice's secret number is 5. So she calculates 2 to the 5th mod 13, which is 32 mod 13, which is 6 mod 13. So the number that Alice sends to Bob is 6. And Bob's secret key is 7. He computed 2 to the 7th mod 13. 2 to the 7th mod 13 is 11. And the number that Bob sends to Alice is B equal 11. Now, Alice takes Bob's number and raises it to her secret number, little a. So that's 11 to the 5th, which is minus 2. 11 is minus 2 mod 13. Minus 2 to the 5th, that's minus 32. And minus 32 is the same as, is congruent to 7 mod 13, because the difference is 39. So the key that Alice calculates is 7. Let's see what Bob does. Bob takes the number he got from Alice, capital A, and raises it to his B. So this is 6 to the power 7 mod 13. So let me calculate 6 to the power 7. 6 squared is 36. Mod 13, that's equal to minus 3. So if you square 6 squared, you get 6 to the 4th. If you square minus 3, you get 9. So 6 to the 4th is 9. So 6 to the 5th is 9 times 6, which is 54. What is 54 mod 13? It's 2. Oh, I'm sorry. Everything I did is correct, except I only calculated 6 to the 5th. I want 6 to the 7th. So let me just do this again. I mean, everything was good. I just confused the 5 and the 7. So I have to calculate 6 to the 7th. 6 squared is 36, is minus 3 mod 13. 6 to the 6th is 6 squared cubed, is minus 3 cubed, is minus 27, which is congruent to minus 1 mod 13. 6 to the 7th is 6 times 6 to the 6th. That's 6 times minus 1, which is minus 6, which is the same as 7 mod 13. So Bob also gets 7. So the secret key that Alice and Bob exchange is the number 7. And everything is good in the world. Ooh. Yeah, here I was calculating. For some reason I stopped at 6 to the 5th, but I needed to go up to 6 to the 7th. So this was all correct. I just stopped the calculation too soon for some mysterious reason. Okay. Problems 4 and 5 have to do with El-Gamal key exchange. So again, we start with a publicly given prime number p, which will be 13, and a primitive root 2. So we have Alice and Bob. And Bob wants to send a message to Alice. So Alice calculates her public key A equal to 5, A equal to 3. And she sends that to Bob. So Bob gets the number A equal 3. Bob's message that he wants to send, the plain text, is 10. He wants to send the number 10 to Alice. So he chooses a random element K equal to 3. And he has to compute two numbers, C1 and C2. So the number C1 he computes is G to the K mod P. G is 2, K is 3, P is 13. So that's 8 mod 13. So C1 that he sends, C1 is equal to 8. C2 is going to be M, A to the K mod P. His M is 10. A is 3 and K is 3. So this is mod 13. So the number C2 that Bob calculates is 12 times 3 cubed, which is 10 times 27, or 270. 260 is divisible by 13. So this is 10 mod 13. So C2 is equal to 10. So the pair of numbers that Bob sends to Alice, C1, C2, is 8, 10. Okay, that's all we had to do in problem 4. In problem 5, it's the El Gamal crypto system with the same prime 13 and the same primitive root 2. So here's Alice, and here's Bob, and Alice's secret key is 4. And the pair that Bob sends to Alice is, and the number, the public key that Alice sends to Bob is 2 to the A, which is 2 to the 4th, which is 3 mod 13. So Alice has gotten the number 3 from Alice. Bob has gotten number 3 from Alice. And the pair that he sends to Alice is the pair 7, 5. So Alice has to decrypt this plain text message. So we have to compute first of all. So M is going to be C1 to the power A inverse times C2 mod P. So what does that mean? C1 is 7. A is 4. So we need 7 to the 4th mod 13. So what is 7 to the 4th mod 13? So 7 squared is 49, which mod 13 is minus 3, was 52. Is 4 times 13. So 7 to the 4th is 7 squared squared, is minus 3 squared is 9 mod 13. So C1 to the A is congruent to 9 mod 13. What is C1 to the A inverse? That is, if we had C1 to the A inverse, the X, that means we're looking for a number where 9X is congruent to 1 mod 13. And if you just start checking X equal 1, 2, 3, you'll see that 9 times 3 is 27 is congruent to 1 mod 13. So C1 to the A inverse, which is 9 inverse mod 13, is equal to 3. And C2 is equal to 5. So C1 to the A inverse times C2, C1 to the A inverse is 3, C2 is 5, that's 15, that's congruent to 2 mod 13. So the number m that Alice obtains equals 2. And that's the answer. Okay. Here we use the fact that numbers non-zero mod p have multiplicative inverses. And the proof of that is exercise 6a. So in 6a, we want to prove that if m is a positive integer and the GCD of a and m is 1, then there exists an integer x such that ax is congruent to 1 mod m. So we can prove this in 2 ways. Proof number 1. By Euclidean algorithm, if 1 is the greatest common divisor of a and m, that implies there exist integers x and y such that ax plus my equals 1, which means for this x, ax is congruent to 1 mod m. So that's one perfectly good proof. Proof number 2, we would say as follows. If we have integers x1 and x2, if ax1 is congruent to ax2 mod m, then the difference ax1 minus ax2 is 0 mod m, which is, factor out the a times x1 minus x2 is 0 mod m. So therefore m, this says m divides a times x1 minus x2, but the GCD of a and m is 1. M and a are relatively prime. So by Euclid's lemma, m has to divide x1 minus x2, or x1 is congruent to x2 mod m. So if ax1 is congruent to ax2 mod m, then x1 is congruent to x2 mod m. So consider the m-1 numbers, a times 1, a times 2, a times 3, up to a times m-1. So these are all numbers of the form ax, and these are distinct modulo m, because if two of these were equal, x1 would have to be equal to x2, and then the difference mod m, and the difference, the biggest difference between any of these multipliers of a is m-1. And they're also not zero mod m, because m doesn't divide any of the numbers 1 to m-1. So if these are distinct mod m and non-zero, these have to be the numbers 1, 2, 3 up to m-1 in some order. So these numbers are congruent in some order to the numbers 1 to m-1. So one of these numbers, a times some x, has to be congruent to 1 mod m. And that's a very nice proof. That's the second proof. Six B was actually to solve a congruence. 11x congruent to 1 mod 29. So all you have to do is keep multiplying 11 by 1, 2, 3, 4, and so forth until you get 1. 11 times 1 is congruent to 11 mod 29. That doesn't work. 11 times 2 is 22. It's congruent to 22 mod 29. 11 times 3 is 33, which is congruent to 4 mod 29. 11 times 4 is 44, which modulo 29, I think it's congruent to 15 mod 29. But just keep looking. 11 times 6 is 66 mod 29. That's congruent to 9. Is that right? 66 mod 29 is congruent to 9 mod 29. I'm sorry, I want 11 times. That is 11 times 6. 11 times 5 is the next one. 55 is congruent to 11 times 6 was 9 mod 29. 11 times 5 is 55. 55 mod 29. 26. Eleven times 7 is 77. Modulo 29, let's see, 2 times 29 is 58. This is congruent to 19 mod 29. 11 times 8 is 88. Wow, where is this? 88 is 87 plus 1. This is congruent to 1 mod 29. So this is the winner. (11x) congruent to 1 mod 29. X is congruent to 8 mod 29. So any number congruent to 8 mod 29 works. Number 7, right? 23 is the sum of powers of 2. Well, the largest will be 16. This is 16 plus 7. 7 is 4 plus 2 plus 1. So this is like 2 to the 0 plus 2 to the first power plus 2 squared plus 2 to the fourth. This is the binary decomposition of 23. 23 as a sum of powers of 2. So how can we compute 3 to the 23 mod 31? Let's see. So 3 to the 23 is going to be 3 to the 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 to the 4th. So that's 3, 2 to the 0, 3, 2 to the first power, 3 times 2 squared, 3 times 2 to the 4th. 3 times 2 to the 0 is 3 to the 1, which is 3. 3 2 to the first power is 3 squared, which is 9. I want everything mod 31. I want to compute 3 to the 23 mod 31. 3 to the 2 squared is 3 squared squared. That's 9 squared. That's 81, which is, what is 81 mod 31? 19 mod 31. Or I could also write this as minus 12 mod 31. 3 to the 2 cubed is 3 to the 2 squared squared. That's minus 12 squared mod 31. That's 144 mod 31. That's 14 mod 31. And 3 to the 2 to the 4th power is 3 to the 2 cubed squared is 14 squared, which is 196. 13 and 196. I think this is also 14. Let's see. 130, 169, or 27. But it's congruent to 14 mod. Oh, sorry, mod 31. I did the calculation. I was looking at 13. 196 mod 31. 31 times 6 is 186. So this is 10. So this number, modulo 31, is 3 times 9 times 19 times 10. So we have to compute that modulo 31. So this is, say, 27 times 19 times 10. 27 is minus 4. Minus 4 times 19 times 10. 19 is the same as minus 12. So that's 48, 480 mod 31. And 31 into 480. I think it goes 15 times. Well, I always like to check because there's so much arithmetic here. So let me just do the problem again, just to make sure I've done everything right. So 23 is the sum of powers of 2. Is 2 to the 0 plus 2 to the first plus 2 squared plus 2 to the 4th. That is, it's 1 plus 2 plus 4 plus 16, which you can check is 23. So I want to compute 3 to the 23rd power mod 31. So 3 to the 23rd power is congruent to, or is equal to, 3 to the 2 to the 0 plus 2 to the first plus 2 squared plus 2 to the fourth. That's the same as 3 to the power 2 to the 0, which is 3, times 3 squared times 3 to the fourth times 3 to the 16th, mod 31. Of course, 3 squared is just congruent to 9, mod 31. 3 to the fourth power is 3 squared squared, which is 9 squared, which is 81. What is 81 mod 31? 62 is 19. Or if you like, minus 12 mod 31. 3 to the 8th is 3 to the fourth squared, which is minus 12 squared, which is 144. What is that mod 31? 5 times 31 is 155. So this is minus 11 mod 31. 144 plus 11 is 155, and 155 is 5 times 31. And 3 to the 16 is 3 to the 8th squared, which is minus 11 squared, which is 121. And 4 times 31, 4 times 31 is 124. So this is same as minus 3 mod 31. So here I have the powers that I need. I have 3 squared, 3 to the fourth, and 3 to the 16th. So this is congruent to 3 times 9 times minus 12 times minus 3 mod 31, which is what? 3 times 9 is 27, minus 12 times minus 3 is 36. 27 is like minus 4, and 36 is like 5. So this is minus 20, which is the same as 11 mod 31. Huh. What did I get? It's not what I got when I did it the other previously. Good, I'd love to check stuff. So let's just double check again. This is written bigger, so it must be clear. 23 is 1 plus 2 plus 4 plus 16. Or 2 to the 0, 2, 2 squared, 2 to the fourth. So 3 to the 23rd is 3 to the sum of powers of 2. 3 squared, 3 to the fourth, 3 to the 16th. So I have to calculate these powers of 2. 3 is 3, and 3 squared is 9. 3 to the fourth is 81. Mod 31 is 19, which is the same as minus 12 mod 31. Because 3 times 31 is 93. So this is okay. Square 3 to the fourth, I get 3 to the 8th, which is 144, which is plus 11 would be 155, which is 5 times this. So this is minus 11. 3 to the 16 is 3 to the 8th squared. Is minus 11 squared is 121. 4 times this is 124, so this is minus 3. So what I'm multiplying here are the numbers 3, 9, minus 12, and minus 3. 27 times 36. 27 is minus 4, 36 is 5. This is minus 20, which is 11. So using this fast binary trick, 11 is the congruence class of 3 to the 23 modulo 31. And that, lo and behold, is the whole exam. So we're done.